Okay, so this lesson is on exponential growth and decay, and it links in with what you know about exponential graphs that we've been doing in the topic. We've been doing since functions in year 11, and also exponential and logarithmic functions in year 12. So on the left here, we've got two graphs: y equals e to the power of x, and y equals 5e to the power of x. So if this is x and this is y. If you can see that the y-intercept is 1 because when x is 0, the y-intercept occurs, and when anything to the power of 0 equals 1. Likewise here, when x is 0, you've got 5 times e to the power of 0, which is 5 times 1, which is 5. So that's why the y-intercept is there. Now with exponential growth, that occurs when k, which is the coefficient of x, is greater than 0. So you could also, if we were to graph, you could say a general equation for this blue graph is y equals e to the power of kx. Alright, where k is greater than 0. And when k is greater than 0, we end up with exponential growth. Alright, now usually in this topic though, we're graphing against time. So the x-axis then is time, and the equation would be y equals e to the power of kt. Okay, similarly the red graph then could be thought of as y equals 5e to the power of kt. Okay, but usually, because in all of these questions here, we're really concerned with when t is greater than 0, we're really going to be looking at that part of the graph there. So these y-intercepts become the initial amount of the initial quantity. So the initial quantity of, say, the mass of a radioactive substance, or that will be more over here, exponential decay, or the initial population of termites, or the initial population of kangaroos, or something like that. So in these graphs here now on the right hand side, you've got where k is less than 0, and you end up with exponential decay. So when k is less than 0, you end up with exponential decay. Alright, so the purple graph there, you can think of that as being y equals e to the power of negative x, or just generally you could think of it as being y equals e to the power of negative kx. Alright, now, or you could just write it like y equals e to the power of kx, where k is negative. So that's why I had over here where k is negative. It would just be written like that again. So the same like that, except also because we're talking about in relation to time, it'd be y equals e to the kt. Okay, and then the graph in green would be y equals 5e to the kt, where 5 is the y-intercept. Just there, you can see that. That occurs when t equals 0. When t equals 0, you've got e to the power of 0, which is 1 times 5 is 5. So there's our y-intercept. And we're just concerned as well when t is greater than 0. So this part of the graph here. Alright. Now, if the rate of change of some quantity q is proportional to the quantity itself, then dq dt equals k times q. Now, you're already familiar with our rates of change from our last lesson. Remember, rates of change is the first derivative. So the rate of change of some quantity q means dq dt. And if that is proportional to the quantity itself, that's saying like that. Proportional is this symbol here to the quantity q. So that means the rate of change is proportional to the quantity. Now, that means it's in the same ratio. So depending on what the ratio is, then you'll get a constant. So you can replace this proportionality symbol with an equal sign and insert the proportionality constant k. So k is just a constant there. So that equation there has a solution of this exponential equation here. So what is the link between this exponential equation and that differential equation linking the rate of change with the proportion, that's saying it's in proportion to the quantity itself? Well, if we start with this equation here, q equals ae to the kt, where a is the initial quantity. So a is a constant, it's the initial amount, And we've already talked about K. K is also another constant, the proportionality constant. Let's differentiate this with respect to T. So dq dt. Now when you differentiate exponential functions, it's the derivative of the power, so the derivative of kt. Remember, k is a constant. T is what we're differentiating with respect to. So the derivative of kt is going to be k, and then we times that by ae to the kt. Remember, we keep the exponential part exactly the same. Now, ae to the kt is equal to q. So that's equal to kq. And that's our equation that we originally started with. dq dt equals kq. So that's why q equals ae to the kt is a solution of that equation. And we've already talked about when k is greater than 0, you get exponential growth, and when k is less than 0, you get exponential decay. Let's have a look at an example from the 2014 trial last year. Julian's house is infested with termites. The population of termites grows exponentially according to this equation, where a and k are constants, you already know that, and t is in days. That's good to note the units there, because for every question the units will be different. When Julian called the exterminator, there were 80,000 termites in his house. 3 days later, the exterminator arrived to assess the house. The termite population had increased to 310,000. Huge increase. Show that P equals AE to KT satisfies dP dt equals Kp. So really, that's one easy mark just by differentiating, showing you doing exactly what I just did on the previous slide. So starting with the equation for the quantity and differentiating it with respect to T. Remember, A and K are just constants. So you get K times AE to the KT. And remember, AE to the KT is just P. So there we have it. dP dt equals Kp. Then part 2 says find the value of K correct to 4 significant figures. So to find K, first we're going to need A as well. We're going to use the information that's in the question there to help us do that. So we've got P equals AE to the KT. Right, now we've been given that there's 80,000 termites, which we'll call initially. When T equals 0, P equals 80,000. So we've got 80,000 equals AE to the power of K times 0, which is 0. And remember, E to the power of 0 is 1, so that means A is 80,000. So we can say our equation is P equals 80,000 E to the KT. Now to find K, we need to use this second bit of information in the question. That 3 days later, when T equals 3, P equals 310,000. So when P equals 310,000, substitute those in. You've got 80,000 E to the power of K times T. Remember, T is 3. So that's to the power of 3K. Solving this equation, let's divide both sides by 80,000. So we get 31 on 8 equals E to the power of 3K. Taking log of base E of both sides means you'll get over on the right hand side here, when you take log of E to the 3K, using your law, you know about log laws, you can bring this power down the front. So 3K log of E, and you know that log base E of E is just 1, so 3K times 1, which is 3K. So solving this equation, log of 31 on 8 equals 3K. Remember, we're trying to find K. Dividing both sides by 3 then, and we'll get log of 31 on 8 divided by 3. And putting that in your calculator to 4 significant figures, you get K equals 0.4515. So our new equation for P becomes 80,000 E to the power of 0.4515T. Okay, so everything from here to here is part 2. Let's have a look at part 3 now. So part 3, when the termite population exceeds 2 million, the damage they cause will deem the house unsafe. After the initial assessment, the exterminator cannot return for another week to treat the house. Is Will there be enough time to save Julian's house? All right, so if the initial assessment, remember, is up here, is when t equals 3. If the exterminator can't return for another week, that's going to be when t equals the initial 3 days of the assessment plus a week after that is when t equals 10. Let's find what the population is when t equals 10. If it is more than 2 million, then the house is unsafe. If it is less than 2 million, then Julian's house can be saved. So, putting that in your calculator, you get 7,310,205 termites. Or, if you were to store this value of k in your A memory, then you would get a better answer for P, because you'd get 7,311,318 termites. Either way, you can see that both answers, both of these numbers, are more, 7 million is more than the 2 million. Please make sure you answer the question. The question for 2 marks is, will there be enough time to save Julian's house? Remember, if the population is more than 2 million, then it is unsafe. So answering the question there will not be enough time to save Julian's house. Therefore, there is not enough time to save Julian's house. Very important to actually answer the question. Okay. Right, so in this HSC question, we've got a colony of bacteria. Initially there are 1,000 bacteria. The number of bacteria after t minutes, t is in minutes, is given by that equation there. After 20 minutes there are 2,000 bacteria. Show that k equals that correct to 4 decimal places. Alright, so starting with our equation, n of t equals 1,000 e, this should be 1,000 e to the power of kt. Then we're going to sub in when t equals 20, n of t equals 2,000. So we've got 2,000 equals 1,000 e to the power of 20k. T equals 20. Okay, now we're solving this for k. We're trying to show that k equals 0.0347. So dividing both sides by 1,000, you get 2 equals e to the power of 20k. Take the log of both sides. And you saw from before, then that just becomes log of e to the power of 20k. Bring the 20k down the front. And then we just need to divide both sides by 20. Because it says show, it is very important that you show every step. And then when you put that in your calculator, log of 2 divided by 20 equals 0.0347 to 4 decimal places. Okay, part 2 then says, how many bacteria are there when t equals 120? Alright, so that's just subbing in t equals 120. So, we've got to rewrite our new formula with k actually. So n of t equals 1,000 e to the power of 0, let me just rub that out, sorry. 0.0347t. And there is our formula. We're going to sub in t equals 20 and n is going to equal, t equals 120, sorry, 1,000 e to the power of 0.0347 times 120. Okay, and that equals 64,000. So just remember, when you get to k here, store that in your alpha A memory. So you can use that exact number in all further calculations. Alright, number 3, what is the rate of change? So that was last lesson we talked about rates of change. Remember, rate of change is the first derivative. What is the rate of change of the number of bacteria per minute? So that means we want to find dn dt. All right, so we're differentiating this formula here. So when you differentiate an exponential function, it's the derivative of the exponent, which is 0.0347, times that whole thing. So it's 1,000 times 0.0347. So 0.0347 times 1,000 is going to move the decimal points 1, 2, 3 places to the right. So that becomes 34.7 e to the power of 0.0347t. So there's our first derivative. Then we want to find what the rate of change is when t equals 120. So when t equals 120, we're going to find dn dt by subbing in 120 for t. Equals. So 34.7, we're going to use the exact number from our calculator using alpha A. 0.0347 times 120. So you will get 2,218 bacteria. This is the units per, what's T this time? T is in minutes, so that's going to be bacteria per minute. Alright, then part 4. How long does it take for the number of bacteria to increase from 1,000 to 100,000? So really this is saying find T when N equals 100,000, because remember it initially was 1,000. Okay? So let me do that in black. We're finding T when N equals 100,000. So we've got 100,000 equals 1,000 e to the power of k, which is 0.0347 t. And we're solving this equation for t. So dividing both sides by 1,000. Let me show you a quick way of doing that. Cross off 3 zeros there, cross off 3 zeros there. So you can see 100 equals e to the power of 0.0347 t. Take the log of both sides. Log of 100 equals 0.0347 t. Divide both sides by 0.0347. Log of 100 divided by 0.0347. So really you're typing in your calculator log of 100 divided by alpha A. And you should get 132.9 minutes. Because remember, t is in minutes. Okay. So the last 2 examples that we've done have been to do with exponential growth. So let's have a look at a question now. Alright, in radioactive materials, the rate of decay of the mass of the substance is proportional to the mass itself. So let's just read that again. The rate of decay of the mass, so that is dm dt, the rate of decay of the mass is proportional to the mass itself. That looks familiar from, I think, the second slide that we had. Remember, that means dm dt equals k, a constant, times m. Alright, a certain radioactive material takes 200 years to decrease in mass from 10 grams to 8 grams. Find the mass of the material after 300 years. Alright, so how can we use this equation to find the mass of the material when we don't even really know the rate of change? Well, because we know that the rate of decay is proportional to the mass, then we can say that the mass is equal to an initial amount, e to the power of kt. How can we just jump straight from this to this? Well, let's differentiate our expression that we have for the mass and see if we get back to the rate. So, differentiating this with respect to t, remember a is a constant, k is a constant. So dm dt is going to be the derivative of the exponential function, so the derivative of kt with respect to t, which is just going to be k, times a e to the power of kt. And a e to the power of kt is equal to m, so this is equal to m So this is equal to Km. So we've got dm dt equals Km, which is what we have here. So this, therefore, is a solution of this differential equation. So let's use this here to help us solve this problem. So m equals ae to the power of kt. All right, m, the mass of this substance, equals ae to the power of kt. All right, it takes 200 years to decrease in mass from 10 grams to 8 grams. So we'll say that 10 grams is the initial mass. So when t equals 0, m equals 10 grams. So this is what this bit's saying. When t equals 0, m equals 10. So then you can say 10 equals ae to the power of k times 0, which is 0. And therefore you can see clearly that a must equal 10 because e to the power of 0 is 1. So our equation then for our mass becomes m equals 10 e to the power of kt. Now we need to find the mass of the material when t equals 300. Before we can get that, we need k. So how do we find k? Well, we're going to use this bit of information here, that when t equals 200, the mass is then 8 grams. So substituting that in, the mass is 8 when t equals 200. So this becomes 200 times k. So let's divide both sides by 10. And then we'll take the log of both sides. And then we'll divide both sides by 200. And you'll get a value for k, which is negative 1.11 times 10 to the power of negative 3, which is the same as negative 0. That's scientific notation that your calculator's showing you. So remember, going from scientific notation to normal numbers, 0.00111. Okay, so moving the decimal point, negative 3 is 1, 2, 3. There it is. So there's our value for k. So our equation for m then becomes 10 e to the negative 0.00111 t. And remember, I'd like you to store this number that you get for k in your A memory. All right, now we want to find the mass. Now we want to actually answer the question, which is to find the mass of the material after 300 years. So when t equals 300, because we're letting t be in years, because the initial time that we were given there was in years. All right, so I might have to try and squeeze this in just here in the middle. So the mass when t equals 300. So m is going to equal 10 e to the power of negative 0.00111 times 300. Okay, simple substitution. And we get 7.2 grams. Grams because the initial weight was in grams and so was the other weight just here. Okay, then part B says find the half-life of the material. The half-life. Some of you, this might be familiar for some of you who do chem. So this is the time. This question is saying find the T when the mass is half its original. So its original mass was 10 grams. So half of that is going to be 5 grams. So this question is saying find T when m equals 5 grams. So when m equals 5, we need to find T. So just substituting into our equation. Here's our equation. Remember we had that down here. And we're just making m equal 5 and we're solving this equation for T. So let's divide both sides by 10. We get 0.5 equals e to negative 0.00111 t. Then we'll take the log of both sides. See the pattern that's emerging here with solving these equations? Negative 0.00111 t. And then because we want to find t, let's divide both sides by our alpha A memory, because that's where our K is, negative 0.00111. And we should get for T 621. And remember, T was up here in years. So that means the half-life of this material is 621 years. Now I've made a little summary of some steps that we just pretty much followed here. You can see that I found A, the initial amount, then we found K, the constant. We rewrote the equation with our A and our K, and then we use that equation to actually solve and answer the questions needed. So, has that summarised for you? Step 1, find the initial quantity. So I've been calling it A, sometimes it's called M0. Little subscript means when T equals 0 or Q0. Find K, store that in your A memory, and then substitute into equation to actually answer the question. That's it.